Question 1. A machine learning model achieves 99% accuracy on its training dataset, but only 60% accuracy on a separate, unseen validation dataset. This scenario is a clear indication of which problem? Option A. Underfitting. Option B. Overfitting. Option C. Data drift. Option D. Concept drift. The correct answer is overfitting. Here's the explanation. Overfitting describes a scenario where a machine learning model learns the training data too well, including its noise, resulting in high training accuracy but poor generalization performance on new, unseen data. The significant gap between training and validation accuracy is the telltale sign. Question 2. Which of the following is a common cause of overfitting in machine learning models? Option A. Using a model that is too simple for the complexity of the data. Option B. Training the model on an excessively large and diverse dataset. Option C. The model having too many parameters or being excessively complex relative to the amount of training data. Option D. Stopping the training process too early, before the model has learned sufficient patterns. The correct answer is, quote, the model having too many parameters or being excessively complex relative to the amount of training data. Here's the explanation. Overfitting often arises when a model is excessively complex for the amount or quality of available training data, or when it has too many parameters, leading it to memorize noise rather than learning generalizable relationships. Question 3. In the context of MLOps, why is early stopping considered an effective strategy to mitigate overfitting? Option A. It adds a penalty to the loss function for large model weights, simplifying the model. Option B. It randomly drops units during training, preventing co-adaptation of neurons. Option C. It monitors validation performance and halts training when it begins to degrade, even if training performance is still improved. Option D. It increases the diversity of the training data through transformations. The correct answer is, quote, it monitors validation performance and halts training when it begins to degrade, even if training performance is still improving. Here's the explanation. Early stopping is a form of regularization, where training is halted when the model's performance on a separate validation dataset starts to worsen, even if its performance on the training dataset is still improving. This prevents the model from continuing to learn the noise in the training data. Question 4. Which of the following scenarios is the most indicative of an underfitted machine learning model in an MLOps context? Option A. The model performs exceptionally well on the training data, but poorly on the validation data. Option B. The model achieves high accuracy on both training and validation data, but deployment is slow. Option C. The model performs poorly on both the training data and the validation data. Option D. The model's performance degrades significantly only after being deployed to production. The correct answer is, quote, the model performs poorly on both the training data and the validation data. Here's the explanation. Underfitting is characterized by a model that is too simplistic to capture the underlying patterns in the data, leading to poor performance on both the data it was trained on and unseen data. Option A describes overfitting, and option D suggests issues like data drift or concept drift rather than initial underfitting. Question 5. An MLOps team observes that during model training, the loss function values decrease initially, but quickly plateaued at a high level. Subsequent evaluation shows high bias and low accuracy on the validation set. Which of the following is the most likely cause? Option A. The model is overfitting to the training data. Option B. The learning rate used during training was too high, causing divergence. Option C. The model architecture is too complex for the given problem. Option D. The model has insufficient capacity to learn the underlying patterns in the data. The correct answer is, quote, the model has insufficient capacity to learn the underlying patterns in the data. Here's the explanation. High loss plateauing early and high bias are key indicators of underfitting. This occurs when the model's complexity, or capacity, is insufficient for the complexity of the problem, meaning it cannot effectively minimize the loss function. Option A describes overfitting. Option B would likely lead to loss increasing or fluctuating wildly, and option C would typically lead to overfitting, not underfitting. Question 6. In a cloud-based predictive maintenance solution, a data scientist uses a simple linear regression model to predict machine failure based on sensor data. However, the model consistently fails to capture complex, nonlinear degradation patterns, resulting in frequent, unexpected downtime. From an MLOps perspective, how would this issue typically be identified, and what is a common solution? Option A. Identified by high training accuracy but low test accuracy. Solved by reducing model complexity. Option B. Identified by low performance during model validation. solved by increasing model complexity or feature engineering. Option C, identified by model latency spikes in production, solved by optimizing inference infrastructure. Option D, identified by concept drift in production monitoring, solved by retraining with more recent data. The correct answer is identified by low performance during model validation, solved by increasing model complexity or feature engineering. Here's the explanation. The scenario describes underfitting, where a simple model fails to capture complex patterns. In MLOps, this would be identified during the model validation and evaluation stages due to consistently low performance metrics. Common solutions for underfitting include increasing model complexity, e.g., using a nonlinear model, or enhancing feature engineering to provide richer input to the model. Option A describes overfitting and its incorrect solution. Options C and D relate to post-deployment issues, not initial underfitting. Question 7. A machine learning model, deployed in an MLOps environment, exhibits very low error rates on its training data, but performs significantly worse on new, unseen production data. What does this symptom most strongly indicate? Option A, high bias, underfitting. Option B, high variance, overfitting. Option C, irreducible error. Option D, data drift. The correct answer is high variance, overfitting. Here's the explanation. High variance, overfitting, is characterized by a model performing exceptionally well on the training data, low error, but poorly on unseen validation or test data, high error. This means the model has memorized the training examples, including noise, rather than learning generalizable rules. High bias, underfitting, would show high error on both training and test data. Irreducible error is an inherent noise, and data drift refers to changes in input data distribution, which could cause overfitting to become apparent, but isn't the direct symptom itself. Question 8. Which of the following strategies is most appropriate for reducing high bias in a machine learning model? Option A, applying L1 per liter 2 regularization. Option B, gathering more training data. Option C, using a simpler model architecture. Option D, increasing the complexity of the model, e.g., adding more layers to a neural network. The correct answer is increasing the complexity of the model, e.g., adding more layers to a neural network. Here's the explanation. High bias, underfitting, occurs when a model is too simple to capture the underlying patterns. To reduce bias, one should increase the model's complexity, for example by adding more layers to a neural network, or using a deeper decision tree. Options A, B, and C are typically strategies to reduce variance, overfitting. Question 9. In the context of the bias-variance trade-off, what is irreducible error? Option A, the error caused by a model being too simple to capture data patterns. Option B, the error caused by a model being too complex and learning noise from training data. Option C, the minimum possible error that cannot be reduced by any model due to inherent randomness in the data. Option D, the error that only occurs when a model is deployed in production. The correct answer is, quote, the minimum possible error that cannot be reduced by any model due to inherent randomness in the data. Here's the explanation. Irreducible error is the theoretical lower bound for model performance, representing the error that arises from inherent noise or randomness in the data itself, e.g., measurement errors, unobservable variables. It cannot be eliminated by improving the model's complexity or training. Options A and B describe bias and variance errors, respectively. Option D is incorrect, as irreducible error exists regardless of deployment stage. Question 10. Which of the following best defines hyperparameters in the context of machine learning and MLOps? Option A, internal variables learned by the model during the training process to minimize a loss function. Option B, the final output predictions generated by a trained machine learning model. Option C, external configuration settings that are set prior to the training phase and dictate the behavior of the learning algorithm. Option D, features engineered from raw data to improve model performance. The correct answer is external configuration settings that are set prior to the training phase and dictate the behavior of the learning algorithm. Here's the explanation. Hyperparameters are external configuration variables for a machine learning model whose values cannot be estimated from the data. They are set prior to the training phase and dictate the behavior of the learning algorithm. Question 11. A data scientist is concerned about their deep learning model overfitting to the training data. Which type of hyperparameter would be most relevant to address this issue? Option A, batch size. Option B, learning rate. Option C, regularization strength, e.g., L1 per liter 2 penalty dropout rate. Option D, number of epochs. The correct answer is regularization strength, e.g., L1 per liter 2 penalty, dropout rate. Here's the explanation. Hyperparameters like L1 per liter 2 regularization strength or dropout rates are specifically used to prevent overfitting by adding penalties to the loss function or randomly deactivating neurons during training. Question 12. In an MLOps context, why is the computational cost associated with exploring different hyperparameter combinations a significant consideration? Option A. It primarily impacts the efficiency of data preprocessing tasks. Option B. It directly influences the number of features used in the model. Option C. It can require significant cloud resources, e.g., CPU, GPU hours, and time, affecting budget and project timelines. Option D. It complicates the versioning of model artifacts in a registry. The correct answer is, it can require significant cloud resources, e.g., CPU, GPU hours, and time, affecting budget and project timelines. Here's the explanation. Exploring different hyperparameter combinations can be computationally expensive, requiring significant cloud resources and time. Efficient tuning strategies are therefore crucial in MLOps for managing costs and accelerating development. Question 13. What is the primary purpose of cross-validation in the MLOps lifecycle? Option A. To permanently split data into a single training and test set for final model evaluation. Option B. To reduce the computational cost of model training by using smaller datasets. Option C. To provide a more reliable and less biased estimate of a model's generalization performance. Option D. To ensure that models are always trained on the entire available dataset at once. The correct answer is, to provide a more reliable and less biased estimate of a model's generalization performance. Here's the explanation. Cross-validation's primary goal is to mitigate the limitations of a single train test split by repeatedly partitioning data, offering a more stable and representative measure of how well a model will perform on unseen data. This is crucial for ensuring models generalize well to production data. Question 14. In a typical k-fold cross-validation process, if k is set to 5, how many times does each data point serve as part of the validation set? Option A. 0 times. Option B. 1 time. Option C. 5 times. Option D. An unpredictable number of times. The correct answer is 1 time. Here's the explanation. In k-fold cross-validation, the dataset is divided into k folds. In each of the seq iterations, a different fold is used as the validation set, ensuring that every data point gets to be in the validation set exactly once across all iterations. Question 15. An MLOps engineer is preparing to train a classification model on an imbalanced dataset. Which cross-validation strategy is most appropriate to ensure that each fold maintains the original class proportions? Option A. K-fold cross-validation. Option B. Leave one out cross-validation. Option C. Time series cross-validation. Option D. Stratified k-fold cross-validation. The correct answer is stratified k-fold cross-validation. Here's the explanation. Stratified k-fold cross-validation is specifically designed for classification tasks, especially with imbalanced datasets. It ensures that each fold maintains the same proportion of class labels as the original dataset, preventing a fold from having too few or too many samples of a minority class, which could skew performance estimates. Question 16. What is the primary purpose of tracking model performance metrics in an MLOps context? Option A. To take a static snapshot of model quality after initial training. Option B. To continuously monitor deployed models, ensuring they deliver value and meet business objectives. Option C. To solely identify and fix bugs in the model's underlying code. Option D. To reduce the computational resources required for model inference. The correct answer is to continuously monitor deployed models, ensuring they deliver value and meet business objectives. Here's the explanation. The study material states, the primary purpose of tracking model performance metrics is to ensure that deployed models continue to deliver value and meet their intended business objectives in dynamic real-world environments. This emphasizes continuous monitoring beyond initial training. Question 17. A data science team is evaluating a machine learning model designed to predict the remaining useful life (RUL) of industrial machinery components. Which set of metrics would be most appropriate for this task? Option A. Precision, recall, F1 score. Option B. Normalized discounted cumulative gain, NDCG. Mean average precision, MAP. Option C. Mean squared error, MSE. Root mean squared error, RMSE. Mean absolute error, MAE. Option D. Accuracy, ROC-AUC, log loss. The correct answer is mean squared error, MSE, root mean squared error, RMSE, mean absolute error, MAE. Here's the explanation. Predicting the remaining useful life, RUL, is a regression problem, as it involves predicting a continuous numerical value. The study material lists MSE, RMSE, and MAE as key regression metrics. Question 18. In the context of MLOps, why is establishing a robust performance baseline during model validation crucial for effective production monitoring? Option A. To reduce the need for continuous monitoring in production. Option B. To simplify the model deployment process by pre-approving performance. Option C. To define acceptable performance ranges against which production metrics can be compared to detect degradation. Option D. To automatically trigger model retraining without human intervention. The correct answer is to define acceptable performance ranges against which production metrics can be compared to detect degradation. Here's the explanation. The study material states, baselines are key. Establishing a robust performance baseline during model validation is crucial for effective production monitoring. Without a baseline, it's hard to determine if current performance is acceptable. This baseline provides the expected state for comparison. Question 19. What is the primary objective of feature engineering in the machine learning lifecycle, particularly emphasized in an MLOps context? Option A. To solely reduce the dimensionality of the dataset for faster model training. Option B. To transform raw data into features that improve model performance, interpretability, and robustness. Option C. To ensure that the machine learning model can be deployed on low-resource edge devices. Option D. To automate the entire model development process without human intervention. The correct answer is, quote, to transform raw data into features that improve model performance, interpretability, and robustness. Here's the explanation. The overview states that feature engineering involves transforming raw data into features that better represent the underlying problem, thereby improving model performance, interpretability, and robustness. It's not just about dimensionality reduction, but about creating more informative signals for the model. Question 20. Which feature transformation technique is most suitable for converting a nominal categorical feature, such as city, e.g., New York, London, Paris, into a numerical format for a machine learning model? Option A. Label encoding. Option B. Standardization, z-score scaling. Option C. One-hot encoding. Option D. Log transformation. The correct answer is one-hot encoding. Here's the explanation. One-hot encoding is the most appropriate technique for nominal categorical data, as it creates new binary features for each category, avoiding the introduction of artificial ordinal relationships. Label encoding is for ordinal data. Standardization and log transformation are for numerical features. Question 21. In an MLOps environment, what critical role does a feature store play in operationalizing feature engineering? Option A. It automatically designs and optimizes new features without human input. Option B. It serves as a centralized, consistent, and versioned repository for engineered features, crucial for preventing training serving skew. Option C. It is primarily used for selecting the most impactful features for model training. Option D. It stores only the raw, untransformed data before any feature engineering is applied. The correct answer is it serves as a centralized, consistent, and versioned repository for engineered features, crucial for preventing training serving skew. Here's the explanation. A feature store is a centralized repository that manages, serves, and versions features, ensuring consistency between training and inference data, which directly addresses the problem of training serving skew and promotes feature reusability. Question 22. A critical principle in MLOps data preprocessing, often tested, is the necessity to apply the asterisk exact same times preprocessing steps and parameters, during which two stages? Option A. Data ingestion and data archiving. Option B. Model training and model inference, serving. Option C. Data exploration and data visualization. Option D. Feature selection and hyperparameter tuning. The correct answer is model training and model inference, serving. Here's the explanation. The exam tips explicitly states, a fundamental concept often tested is the absolute necessity to apply the asterisk exact same preprocessing steps and parameters during both model training and inference, serving. Discrepancies lead to training serving skew and degraded model performance in production. Question 23. Which of the following data preprocessing techniques is primarily focused on converting categorical variables, e.g., red, green, into numerical representations that machine learning algorithms can process? Option A. Data cleaning. Option B. Feature scaling. Option C. Categorical encoding. Option D. Dimensionality reduction. The correct answer is categorical encoding. Here's the explanation. The key features components section defines categorical encoding as converting categorical variables, e.g., red, green, blue, into numerical representations that machine learning algorithms can understand. Question 24. What is a common consequence of poor data preprocessing in an MLOps environment? Option A. Reduced computational costs for model training. Option B. Improved model interpretability. Option C. Increased model accuracy and faster convergence. Option D. Model bias, poor generalization, or slow convergence. The correct answer is model bias, poor generalization, or slow convergence. Here's the explanation. The overview states, without robust data preprocessing, even the most sophisticated machine learning algorithms will struggle to deliver accurate and reliable results, making it a cornerstone for production-grade 1050 systems. It also explicitly mentions preventing issues like model bias, poor generalization, or slow convergence. VID exam tips also note that poor preprocessing can lead to biased models, slow convergence, or outright failure. Question 25. What is the core objective of MLOps? Option A. To develop new machine learning algorithms and models. Option B. To focus solely on data collection and preprocessing for ML projects. Option C. To standardize and streamline the life cycle of machine learning models, from experimentation to deployment, monitoring, and continuous improvement. Option D. To replace data scientists with automated systems for model creation. The correct answer is to standardize and streamline the lifecycle of machine learning models, from experimentation to deployment, monitoring, and continuous improvement. Here's the explanation. The core objective of MLOps is to bridge the gap between data science and operations teams, ensuring ML models can be built, tested, and released faster, with greater robustness, reproducibility, and scalability, by standardizing and streamlining their lifecycle. Question 26. Which MLOps component is responsible for continuously observing model performance, data drift, concept drift, and resource utilization in a production environment? Option A. Automated model training. Option B. Model registry and management. Option C. Model deployment strategies. Option D. Model monitoring. The correct answer is model monitoring. Here's the explanation. Model monitoring is explicitly defined as continuous observation of model performance, data drift, changes in input data distribution, concept drift, changes in the relationship between input and output, latency, and resource utilization in production. Question 27. In an MLOps pipeline, what typically triggers a new retraining cycle for a deployed model? Option A. Manual intervention by a data scientist who wants to test a new algorithm. Option B. Detection of significant performance degradation or new, relevant data becoming available through continuous monitoring. Option C. A scheduled daily backup of the model artifacts to cloud storage. Option D. A change in the version control system for the model's inference code. The correct answer is detection of significant performance degradation, or new, relevant data becoming available through continuous monitoring. Here's the explanation. The documentation states that if monitoring detects a significant drop in performance, or if new, relevant data becomes available, the MLOps system can automatically trigger a retraining pipeline. Question 28. What is the fundamental reason MLOps is needed, stemming from the inherent complexities of machine learning projects? Option A. To eliminate the need for data scientists in ML development. Option B. To simplify traditional software development processes for non-ML applications. Option C. To address unique challenges like reproducibility, model versioning, data drift, and continuous retraining that are not typically found in traditional software. Option D. To exclusively focus on the research and development of new ML algorithms. The correct answer is to address unique challenges like reproducibility, model versioning, data drift, and continuous retraining that are not typically found in traditional software. Here's the explanation. MLOps is needed because ML systems present unique complexities compared to traditional software, including managing data, models, features, and their relationships, along with challenges like reproducibility, model degradation, and continuous iteration. Question 29. Which MLOps component directly addresses the problem of models becoming stale and less accurate over time due to changes in real-world data distributions? Option A. Experiment tracking and management. Option B. Model versioning and registry. Option C. Continuous training, CT. Option D. Infrastructure as code, IAC. The correct answer is continuous training, CT. Here's the explanation. Continuous training, CT, addresses the problem of model staleness and drift by automatically retraining models on new data, often triggered by performance degradation or scheduled intervals, to maintain accuracy and relevance. Question 30. A key benefit of implementing MLOps is improved reproducibility. How does MLOps primarily achieve this? Option A. By focusing solely on developing new, more robust ML algorithms. Option B. By ensuring that only the latest version of a model is ever used. Option C. By applying version control not only to code but also to data, features, and models, along with comprehensive experiment tracking. Option D. By requiring manual approval for every stage of the ML lifecycle. The correct answer is by applying version control not only to code but also to data, features, and models, along with comprehensive experiment tracking. Here's the explanation. MLOps aims for full reproducibility by applying version control to code, data, features, and models, and through comprehensive experiment tracking, ensuring that anyone can recreate the exact same model output. Thanks for watching. Please subscribe to my channel.